Chapter 6 is basically a bunch of classical applications of the integral. Okay, so it's it's a bunch of problems that you can do using integration. So we'll be doing things like finding areas, finding volumes. These volumes will be of a particular sort. They're called volumes of solids of revolution. Solids of revolution. So you take some object, sort of object, like a circle, say, a disk, and then you take some axis of revolution, and you rotate that object around the axis, right? You rotate that object around the axis, and then you get some sort of, you get something, right? And you want to know what's the volume of that thing that you rotated around. So actually, this is the wrong picture. If I have a circle, and I rotate it around. I rotate it around an axis, then I end up with something like a donut, right? I end up with this donut. How do you find the volume of the donut? So we'll be doing that sort of thing. We'll also be doing surface areas. Surface areas. Okay, so like, what is the area? What is the surface area of that donut? Or what's the surface area of a cone? This type of thing. So it's a bunch of sort of things that you can do with the integral now that we have it. Okay. So so we'll just start off with something very simple, which is area between curves. Okay, so I think you've probably all seen this sort of thing before. So a typical sort of problem is you have one curve, and then you have another curve, right? And you want to find the area between those two curves. Okay. So how do you do it? How would you do it? So let me just give an example. Let's say that the guy going up is, suppose they're both parabolas. The guy going up is like this. The guy going down is this. Okay, and you want to find the area that's trapped between these two parabolas. Right? I think most of you have seen this sort of thing before, so I'm just going to ask you to take a minute and do it, and then we'll talk. Take a minute and try to find the answer. What's the area trapped between these two objects? Okay, turn to somebody nearby and talk with them, please. Okay. Okay, so would somebody like to explain to us how do you find this area? How do you find this area? Anybody want to explain it to us? Suppose I asked you for the area under this top guy. How would you find the area under that? Well, that would just be the integral, right? You would just take the integral from whatever this is to whatever this is, right? You take the integral from here to here of that upper guy, right? And that would give you this area, right? Well, we want the area between them, right? So we need to subtract off the area that's beneath the lower guy, right? So we would get the area of the upper guy, which is F, between A and B, and we subtract off the area beneath the lower guy, right? In other words, the area between the upper guy, what we call the upper guy U, and the lower guy L, over the integral AB, is going to be the integral from A to B of the upper guy minus the lower guy, right? Right. That's going to be the area, right? Okay. Right. Or you can just think of this thing. U minus L is this distance, right? U minus L is this distance, and we're integrating that distance. We're integrating that distance from A to B, right? Okay. So this is the upper guy. This distance here is the upper guy minus the lower guy. Okay. Okay. So did somebody get somewhere on this? Somebody get it? How do you get it? Well, you need to figure out the bounds of the integration, right? So who wants to tell us about it? Anybody? No? Franco.
So just an equation.
Yeah. Right. Just say
x squared minus 9x plus 10 equals negative 2x squared plus 4.
right. Right. So you find the points of intersection. Right. Find the points of intersection by setting them equal to each other. It ends up to be 1 and 2. Right. So x ends up to be either 1 or 2. Right. You use the quadratic equation. Like move these guys to one side. Use the quadratic equation on it. Same. If you need. Right. So you figure out that this is 1 and this is 2. Right. And then you just integrate the upper guy minus the lower guy from 1 to 2. Okay. Right, and I'm not going to do that. You can do that. I assume you can do that. Okay. Right. Makes sense. Right. Define the area. Area chap between two curves. You integrate the height of the difference. Right. You integrate the difference. Okay. Okay. Let me do one that's a little bit different, just slightly different. Suppose we have this situation, x equals y squared plus 6, and x equals negative y squared plus 14. Okay, and I want to find the area between these two parabolas. Okay, so again, take 1 minute and see if you can do it. Okay, turn to somebody nearby and tell them how you set it up. Okay. Would somebody like to talk to us about it? Anybody? How about Kate? Do you want to talk? Would you mind talking?
Sure.
Great, thank you.
Well, I set the two equal to each other first.
Sure. So, what does your picture look like? Well, you've got one parabola going this way, right? And you've got another parabola going the other way. You've got another parabola going that way, right? Okay. So then you set them equal, and you found that the intersection is
-2 and 2.
-2 and 2, right? So let y squared plus 6 equal -y squared plus 14. You see that y is going to be plus or minus 2, right? So from -2 to +2, the y.
And then I integrated in terms of y.
You integrate it in terms of y, exactly, right? So you're going to integrate, well, let's see, this is the guy on the right. So let's call this guy f of y is y squared plus 6, right? And the guy on the left we're going to call g of y equals -y squared plus 14. And so what do you integrate?
The f of y minus 2.
Yeah, you integrate the right guy minus the left guy, right? Because you're looking for this distance, right? You're going to take this distance, the right guy minus the left guy, dy, as y ranges from -2 to +2. Okay. Okay. Everybody okay with that? Right? So, I mean, this, maybe I should write it out. Right, it's the guy on the right minus the guy on the left, dy. Right. In terms of, if we think of this as a limit of Riemann sums, what we're doing is we're chopping this thing up into little pieces. We're taking these distances and then multiplying by the widths of those pieces, right? And so we get get something like this, and then you take the limit of that, and that's going to be this integral, right? Okay, right. Over here, we did something different. Right? We chopped this way, and then we took these approximations and then took the limit, right? Okay, everybody okay with that? Okay. Now this thing, although I've drawn it incorrectly, the x values are the same, right? It's going to be the x value is 10, right? At -2 and +2, the x value is 10, right? So this is 10 comma -2. This is 10 comma +2, right? So if you felt like it, you could have written this as an integral like this, right? You could have written this as an x integral if you felt like it. You wouldn't want to, right? But suppose if you wanted to, you could. See if you can. Take 30 seconds and write down what the integral would be right? You've got this upper function and you've got this lower function, right? What's the upper function? What's the lower function? Right? You can write this, right? So this is 6 and this is 14. Okay, turn to somebody nearby and talk with them, please.
Yeah, exactly.
Okay, would somebody like to talk about it? How about Jantima? No? Okay. Laura Epperson. How about you? Do you want to talk? You don't have to? No? That's okay. Would somebody like to volunteer so I can stop putting people on the spot? Yes, Elizabeth.
I don't know at all if I did this right.
That's okay. That's great. That's the right way to begin.
I would do it in like 2 sections.
Yeah. Right.
So I would do like the integration from 6 to 10 of
This upper guy minus
Yeah.
the lower guy.
In
So what's the
terms- in terms of x.
yeah.
So I think it would be the square root of x minus 6 dx. And then you would add the from 10 to 14 of the second one.
Okay. So let's think. So let's look at this first one first. So you say, okay, I've got this area here. The area is the thing between this function and this function, right? Is the area between this function and this function. Well, what's this function, right? What's this function, right? X is y squared plus 6, so as you say, right, that means that y is going to be the square root of x minus 6, right? So that's for the upper guy. But what do you subtract off then? What's the lower guy? What's the equation for for this? Yes?
It's just negative.
Negative, right? So minus negative, right? The equation for the lower guy is negative. Right? This thing up here is the graph of the upper guy, which is the square root of x minus 6, and this is the graph of negative the square root of x minus 6, right? So you get minus negative the square root of x minus 6 dx. Okay, right? In other words, you get the integral from 6 to 10 of the square root of I'm sorry, 2 squared roots of x minus 6. Okay. And then you'd have to do the other part. Well, the other part would be the integral from 10 to 14 of, oh, what's that going to be? You need the upper guy. Well, that's going to be 14 minus x's square root, right? And negative of that, right? So we'll get, the upper guy minus, again, the lower guy. Okay, so you get plus twice the integral from here of the square root of 14 minus 6 dx. Dy, dx. Right. Okay. Question, yes?
Yeah. What if they were not symmetric with respect to the axis?
Yeah. So what happens if we have something like the intersection is here and the intersection is here,
Yeah.
right?
Symmetry, so
Yeah, then it's more so in that case, there's almost no reason to switch over to the x, right? That way would be so much better. This way you would have to break up into 3 parts, right? You'd have to break it up into this part, into this part, and into this part. So you have 3, you have to break it up into three integrals, right? Because of the symmetry, it's not too bad, but yeah. Okay, everybody seeing how, yeah, I am good.
Yeah, I was trying to figure out how you got the formulas from the graph.
How I got
Like
the formulas for what?
Like square root of x minus 6.
Oh, okay. So here we have this guy here, which the graph is this thing, right? X is y squared plus 6,
And that was given.
right? That's given to us, right? Here's what we were given. We're given 2 parabolas, and we wanted to find the intersection. We wanted to find the area between the 2 parabolas. Okay, that's right. And so we say, okay, well, we want to write this as a function of x, right? Right. What's the y value as a function of x? Well, the y, you just solve for it. Right? You say, well, y squared is x minus 6. So that means that y is plus or minus the square root of x minus 6. Right? For this part, it's the y equals plus the square root of 6. For this lower part, it's going to be y equals minus the square root of x minus 6. Right? And so that gives you your 2 functions, your upper function, right? We'll call this guy u of x. We'll call this guy lower function of x. Okay. Is that okay?
Yeah. That's good.
Yes, Jessica.
Did you label the right graph wrong? Because you switched it on the left graph.
Oh, yeah.
Okay.
Yeah, I got it backwards. This guy is the left guy, right? This is
So on top.
this is the left.
Okay.
Right, this guy is the right guy. Yeah, thank you. Yeah. So, yeah, so this should be this is backwards, thank you. Right, we get the right guy minus the left guy. Yeah, thank you. Yeah, thanks.
So is that the opposite?
No, this is this was the wait, so this guy is the left guy, and this is actually correct.
Okay.
Yeah.
So the previous one was right? The y squared plus 6 minus negative y plus 14?
No, because we need to take the right guy.
Isn't it the left minus the right?
No. If you take the left minus the right, you're going to get a negative distance, right? Like, what's the distance from from 1 to 3, do I take 1 minus 3, the distance is -2. No, you take the number on the right minus the number on the left to get this distance. It's correct now. Okay. Okay, one last example. X equals y squared and x equals y plus 2. Okay. So you have a parabola, right? And you have a line. Okay. Okay. So take a minute and write down an integral to evaluate this. Okay, turn to somebody nearby and talk with them, please.
Okay, yeah.
You're trying so slowly, but I got no this one, so it'll be linear 1 minus this one minus, and then this one,
Yeah, I was just, I multiplied by -1 to 2 here, the right one, which is y plus 2 minus.
Okay. Okay.
Because I just, okay, this is.
Okay, who would like to tell us about it? What are you going to integrate in? X or y? Y. Right? Because then you've just got one, you'll have one integral, right? You go from this y value to this y value, whatever it is, right? So you work it out, right? You see that this point is 1, -1, this point is 4, 2, right? And so you could, if you felt like it, you could do it as an x integral, as two x integrals, right? From 0 to 1 would be 1, right? From 0 to 1 would be one integral. From 1 to 4 would be another integral, right? But it's probably easier to do it as a single y integral, single integral in y from -1 to 2, right? So you say, okay, I'm going to go from -1 to 2. I want to take my right function minus my left function, right? Right. So, right. So what's my right function? What's it going to be? y plus 2, right? Right? And then minus y squared. Right? Negative 1 to 2. Okay, so that's enough of that, I guess. Let's go on to the next thing, which is finding volumes. Okay, finding volumes. Okay. So here's the, suppose you're in elementary school. Go back to elementary school, and your teacher has just finished teaching you about volumes of just like volumes of simple things like blocks and stuff. Okay, and then the teacher comes out and says, "What is the volume of this?" and hands you a loaf of bread. Okay, so how do you figure out the volume of that loaf of bread? How do you figure out the volume of the loaf of bread? Right. Well, maybe one way you could do it. So you've got this loaf of bread. Okay. Is that bread? I have. Okay, you've got this thing, this loaf of bread. It's kind of bumpy. Okay, you've got this loaf of bread.
It's a good bread.
All right, thanks. You're very kind. You've got this loaf of bread, right? How do you figure out the volume? Well, maybe one way you could do it is to slice it into slice it, take it and then slice it into slices. Okay, right? And then you take each slice and put it on a piece of graph paper, right? So you have your graph paper, you put it down, and you trace it, and you say, okay, I know the area of that slice, right? And you try, maybe you slice it in 1 centimeter thicknesses, right? So you would say, okay, I've got my graph paper. I figure out how many square centimeters this guy was. I say, okay, I'm going to multiply that by 1 centimeter, and that's roughly the volume of that first slice, right? And then you do that for the second slice, the third slice, et cetera, right? And that would give you some approximation of it, right? But that's not quite right because the bread maybe is, the bread changes area between, it's the bread isn't perfectly straight, like this, right? The bread has some angles to it, right? Okay, so then you would slice. You say, okay, well, maybe that's not so good. I'm going to slice it in half centimeter slices and do the same thing, and go on and like this. And what you'd be doing is the same thing as Riemann sums, right? And in the limit, you would get some number. In the limit, you'd end up with some number that approaches your actual volume. Okay, so that's the idea of volume, right? The volume, if you have, let A of x denote the area of a cross section of your solid. Right, so you have this thing. Here's the x-axis, right? And at each x, you slice through your object, right? You slice through your object, and you get this cross section, right? The area of that cross section we're going to call A of x. Okay, right? Then we define the volume of the object. The volume of the solid, well, it's going to be the integral from, let's say you start at A and end at B here, right? The integral from A to B of ax dx, right? Because this is the limit. This is the limit of those Riemann sums that you just did back in time. So just to give a simple example, and this example you know already, right? If I have a cylinder here, right? I have a circular cylinder here, right? I have a circular cylinder of radius 3. Well then, every time I cut through it, the area of the cross-section right? What's the area of the cross-section? Kristen?
Pi r squared.
Pi r squared, right? Pi r squared, right? 9 pi, right? And so the volume, right? So the volume then is going to be the integral from 0 to 10 of this area dx, right? And so you get the integral of 9 pi from 0 to 10 dx, right? In other words, you get 90 pi. Right? That would be the volume of the cylinder, which you knew already, right? Pi r squared times height is the volume of the cylinder. But we're basically deriving the formula here. If you didn't know the formula, you could figure it out this way, right? You get pi r squared times the length of this integral. In other words, the height of the cylinder. Okay. Is everybody all right? Everybody all right with that? Okay. Now, suppose we have something like this. We have something that is radius 3 here and radius 5 here. Okay, so it's part of a cone. Right. So let's say that this goes again from 0 to 10. Okay. If I cut through at time x, right? If I cut through it at distance x, take 1 minute and tell me what the area is going to be, right? So that we can figure out the volume. I know you probably have a way of figuring out the volume other ways, but let's do it this way. Okay, talk with somebody nearby. Tell them what you wrote down for the area.
I got so the slope of this line is going to be 2 times x. So that's 3, yeah, because it rises 2 over. Yeah, that makes it easier.
Okay, so Marie Claire, how about you? Since I hear you, I can hear you.
Okay.
Yeah. So what's the answer? A of x is going to be
2/10 of x plus 3 squared times pi.
right. Right. So this is your r. Right. This is your radius at time x. Why is that your radius at time x?
Because it rises 2 units over 10.
Right. Because you know the slope of this line, right? Right. You've gone up 2, right? You've gone up 2 units in 10 units time, right? So the slope of the line is 1/5, right? So by the time we're at x, we're at 3 plus x times 1/5. Right? So this is a good junior high school problem. Right? Is that right? Yes. Right, you guys learned sloping around junior high school, or maybe before that? When do you learn about slope? I don't remember. It's too long ago. Okay. Okay, right? Okay, so this is the area, right? And then you would just take the integral from 0 to 10 of this thing, right? Pi r squared dx, right? And then that would give you the volume of the truncated cone. Yes, Elizabeth?
On homeworks and tests and
Yeah.
things, do you want us to just leave it in integral format or solve it all the way out?
Well, you should solve it out. Yeah, I'm not doing it here because I assume you can do it, but I don't want to use class time for it. But definitely solve it out as. Yeah. And on the exams, often on exams, I'll have something really, some sort of crazy integral, and I'll just say set it up, but don't evaluate it.
Okay.
Yeah. So I just want to see if you can figure out what the integral should be. Yeah. Okay. Okay, let's stop here for today. We'll do more of this next time.